We're up at Leaburg, standing next to Leaburg Lake with the Leaburg Dam in the background. It is impressive to look at the Leaburg Dam facility from the perspective of the time in which it was built. And the planning for this project took place in the early 1920s, a period of time when they were in our community just starting to electrify. The value that a project like this provided to our community originally was really quite transformative.
The Leaburg Hydroelectric Project helped power the development of Eugene and the McKenzie Valley. For nearly 100 years, Leaburg's dam, canal, and powerhouse have served our community with clean and reliable electricity. Today, though, the Leaburg project has structural problems due to its age and original building materials and methods. That's why EWEB is investigating the best alternative for the future of the Leaburg Hydroelectric Project. We are working with teams of construction engineers, geotechnical and dam safety engineers, consulting fisheries biologists, hydrologists, and water quality specialists, and speaking with community members to calculate the financial costs and the potential environmental and social impacts of repairing the project. We are approaching this complex problem with a triple bottom line assessment to figure out the best decision for EWEB customers, the folks upriver, and the McKenzie River itself. It is important to note that throughout the process, safety is our first consideration, and the canal is currently stable and there is not an immediate safety risk. EWEB dewatered the canal in October 2018 at the direction of the Federal Energy Regulatory Commission in order to study and begin repairing some of the structural issues. Since then, the only water in the canal comes from stormwater that enters the canal directly as precipitation or comes from the creeks that flow into the canal from the north side of the McKenzie Valley. The canal carries these tributary waters and other stormwater runoff back to the McKenzie River at the Forebay bypass near the powerhouse. EWEB is already implementing repairs so that the canal can continue to serve its stormwater conveyance function, keeping the watershed connected. For the future of the project, EWEB's elected commissioners must decide between making the investments necessary to return to service for power generation or to decommission the facility, reducing the role of the canal to stormwater conveyance only. In this video, we'd like to illustrate how EWEB generates electricity at the Leaburg project, explain the structural issues with the canal, and describe the alternatives we're examining for the future of the Leaburg Hydroelectric Project. Thanks to the Cascade Mountains and Canadian Rockies, we in the Pacific Northwest can get most of our electricity from hydropower. 20 miles east of Eugene, up the McKenzie River, EWEB's Leaburg Hydroelectric Project can power up to 13,000 single-family homes. To generate power, the Leaburg Dam diverts up to 19,000 gallons of water each second into the Leaburg Canal. The water flows at roughly the same elevation through the 5-mile-long canal before dropping with force into the Leaburg powerhouse, spinning 2 turbines that generate electricity for Eugene homes and businesses. Under optimal conditions, the project generates 15.9 megawatts and on average generates enough energy to account for 4% of EWEB's electricity needs. To divert the McKenzie River into the Leaburg Canal, the Leaburg Dam creates a 40-acre reservoir called Leaburg Lake. The lake extends to the EWEB boat landing, which is open to the public. The dam also serves as a bridge and provides an opportunity for fisheries biologists to separate hatchery fish from wild fish to prevent genetic mixing at spawning grounds upriver. The lake also provides the Leaburg hatchery its water intake site. The Luffman Spillway is the closest point between the canal and the river and can be used to drain the canal in an emergency. When it was built in 1928, the canal intercepted several creeks from the north side of the valley. It carries those tributaries onto the McKenzie. Cogswell Creek is where the McKenzie hatchery draws its water. Johnson Creek is the largest tributary. The canal's embankment slopes continue to get taller and taller as it follows the valley, keeping the water elevated above the McKenzie to preserve the greatest amount of drop for the powerhouse. By the time the canal reaches the Powerhouse Forebay, the water is about 80 feet above the river. The forebay directs the water into the powerhouse when EWEB is actively generating power, or directs flow through the siphon spillway when the power plant isn't operating.
The dam was constructed back in 1928, very cleverly located at a prime location on the McKenzie River where it had very good bedrock foundation materials. So they put a tremendous amount of effort into designing a facility that was built to last and take advantage of the hydroelectric resource that it presented for the community.
EWEB has served electricity to Eugene since 1911, when the Eugene Water Board took over management of the Walterville Power Plant to power pumps for its water distribution system. The board started selling excess electricity to local businesses and started serving Walterville customers in 1915. And by the 1920s, the electric side of the utility had over 3,000 customers and needed to find new sources of hydropower. On June 28, 1927, Eugene voters approved the board to create the Leaburg Project. Construction began the next year.
The dam itself was conservatively designed and built with fairly massive concrete pours that we monitor and put a lot of attention into. They've performed really well through all the floods that have come through the dam since it's been in operation. We inspect the downstream toe of the dam frequently, looking for any kind of deterioration to the concrete or to the bedrock.
Construction crews used dynamite and steam-powered machines to blast the bedrock and quarry the stone to build the dam. They made the cement on site, and the structure is still solid to this day.
Everything up at the dam has performed really well and has needed minimal maintenance attention. The dam consists of these 3 roll gates for flow passage into the channel of the McKenzie, and it has an intake for the canal, which allows us to divert up to 2,500 CFS into the canal. We operate the dam to maintain a uniform water surface elevation all year long. So whether it's summertime or a flood condition, we're operating the 3 roll gates to maintain a flat lake surface elevation.
The Leaburg Dam and its fish ladders provide an opportunity for fisheries managers to remove hatchery-born fish from the river to prevent their genetics from interfering with wild populations. Although the dam's main purpose is to divert water into the Leaburg Canal, its role in fisheries management is a major consideration for the future of the Leaburg Hydroelectric Project.
Oregon Department of Fish and Wildlife, National Marine Fisheries Service, and the Corps all use this facility for monitoring fish populations in the McKenzie because it's really hard to capture fish and try to get population estimates. So they've been running this is called a screw trap. So fish that go into the canal get screened out, go through this flume, and when this is dropped into the flume, it just turns and it dumps the fish over into this live well over here. And actually, when I was a young biologist, I worked at this. I ran that track for 5 years or something.
Downstream of the dam, the canal passes by several farms and homes before it carves through the Luffman Bluff.
This is a Luffman Bluff, I think they would call it, but it was a big chunk of basalt that they had to blast through, and it's the first place where the canal runs into bedrock between the lake and here. It was primarily built through alluvial soils, so lots of gravel, sands, and cobbles.
Here, the canal is close to the river, and so it's a convenient location for a safety release valve where the canal could be emptied into the river if downstream water levels get too high, or if there were an earthquake detected.
The function of it is to basically serve as a safety valve for the canal. In 2007 or so, we added another function to this, hooking it up to an automated system we called the Hazard Mitigation Control System. It consists of 4 monitoring stations downstream along the canal where they're constantly watching the water level, and they know what the normal range is between low canal flow and high canal flow. And so that hazard mitigation control system was set up so as soon as that was detected, it would alarm, and then if nobody intervened, this gate would automatically open to relieve water into the canal. One other thing I'll mention here is the Pacific Northwest Seismic Center has a seismic sensor mounted into the bedrock here, so they're monitoring for earthquake here all the time.
From the Luffman Spillway, the canal continues along the north side of the valley, collecting tributary waters from several creeks.
So we are about 2 miles down from the dam now, and the canal has intercepted quite a number of creeks already, but this is the first big one, and this is Cogswell Creek. Cogswell is the second largest creek that feeds in.
Some of the water from Cogswell Creek goes to the McKenzie hatchery to incubate salmon eggs.
And the Cogswell water is really valuable to them. I guess it's the smell of the water that the fish will cue on when they return and try to find the hatchery a few years down the road.
To build the Cogswell reach of the Leaburg Canal, the canal builders excavated and piled up the on-site materials.
This is, I'll talk a little bit about how the canal was built. It was built with the materials that were here. So it's river deposits, gravels and sands, overlain by some finer grained clays, and then some more gravels and sands. The construction specifications had them doing, for the time, good compaction on the portion of the embankment that was going to see the head from the water, and then as you get further away, they didn't require as much compaction, not as many passes with a horse and buggy, because literally that's how they did it.
Because of the antiquated compaction methods during the original build, the Cogswell reach of the canal has allowed seepage dating back to 1930. The internal erosion at this section is what caused FERC to impose a shutdown of the Leaburg project.
The last remediation work we did is when we discovered that the canal construction was just fundamentally flawed, and we knew we would have to do something pretty major to remedy it, and we had a plan for what to do there, which would have worked fine, but unfortunately the internal erosion discovery demonstrated it had progressed further than we could tolerate. And so when the canal initially went out of service, our intent was to do the subsurface investigation, figure out what the repair needed to look like, and then implement it the following summer. And in the course of doing the subsurface investigation, we encountered very soft soils in the foundation. Very soft soil like that translates into is seismically unstable soil. And that means that if we had an earthquake, then we would expect substantial subsidence of the embankment. So FERC wouldn't let us repair this without addressing the seismic issue. And that's what kind of started the whole conversation about, are we gonna invest in the canal to maintain its operation for the remainder of its license period, or are we going to do something else?
Continuing downstream of Cogswell Creek, the canal collects a few smaller tributaries, including Hanson Creek. As the canal approaches the town of Leaburg, it also meets up with Johnson Creek, the largest tributary that flows into the canal. The Federal Energy Regulatory Commission oversees EWEB's operation of the Leaburg project. FERC requires EWEB to demonstrate that the canal could withstand a probable maximum flood, which would essentially occur from a once-in-a-million-year rainstorm. In such a flood, Johnson Creek could put out as much water as the canal at maximum operating capacity.
That is a biblical type storm. It's beyond anything almost imaginable. But If we're operating as a FERC project, you need to demonstrate how you're going to convey that along with the peak flow from Cogswell, as well as all the little creeks, safely back to the river without overtopping your embankment. So even the return to service scenario involves improvements that will eliminate that possibility of overtopping during a PMF, and most likely would involve creating a new spillway, probably not all that much different than what you saw at the Wasteway Gate here, because just on the other side of the embankment is the old stream bed for Johnson Creek.
From Johnson Creek, the canal walls get steeper and cut through sections of bedrock. This is the Ames Reach, and it also has structural issues that must be addressed, including seepage, poor compaction, and liquefiable colluvial material that would be vulnerable to an earthquake.
As I was explaining at Cogswell we had very soft soils. At Ames, there's a foundation layer that is, I think it's described as a colluvium material that is liquefiable and creates another situation where we have seismic vulnerability that is added to at this location by the fact that the slopes are very steep. They were able to create the steep slopes because they had this very bony boulder material, but steep slopes and seismic events don't go together well. So,
at the end of the Leaburg Canal, the power plant Forebay directs water into the penstock intake when generating, with excess flow passing through the siphon spillway.
Another well-sited facility. They built this Forebay structure on a really nice basalt outcrop, very, very solidly anchored foundation.
Finally, when in operation, water enters the Leaburg powerhouse, where 2 Francis turbines are connected to generating units with a total installed capacity of 15.9 megawatts.
You were wondering where the water goes for the power generation. Pair of penstocks under the highway, under the parking area, into 2 generating units. And then you have our tail race. And at the far end of the tail race is a fish barrier, and they leave it open except during salmon migration season, and then they lower it down to keep the fish from getting confused. Because oftentimes, you know, if the barrier isn't there, they want to go see where all that water's coming from.
Now that we understand how the Leaburg project works and the causes of the structural issues that prompted FERC's deactivation orders, let's take a look at the alternatives EWEB is considering for the future of the project. The alternatives range from a full decommissioning of the project to a full return to service, with an option to partially decommission the project while maintaining the canal's stormwater conveyance function, and an option to partially return to service with a lower generation potential. Alternative 1 is the full decommission option. This alternative would return the site to pre-construction conditions, including removing the dam and building a new bridge, restoring Leaburg Lake to river form, removing the canal, and repatriating tributary creeks to the river. Alternative 2 is the full return to service option. To bring the project back to full generation, EWEB would have to remove and replace the Cogswell and Ames sections of the canal to eliminate the seepage issues and seismically vulnerable soils. The rest of the canal would be lined with a non-permeable, high-density polyethylene, or HDPE, liner. Alternative 3 is the partial return to service option that would propose to build a new hydropower house near the Luffman Spillway with a nameplate capacity of 6.2 megawatts. This would allow EWEB to continue to use its 2,500 cubic feet per second water right, and also prevent the need to remove and replace the Ames Reach, which would be quite expensive given the amounts of earthwork required. The 4 miles of canal downstream of the new Luffman Powerhouse would be repaired and altered to carry only stormwater from tributaries. Alternative 4 is the partial decommission option with preserving the canal's stormwater conveyance function. To achieve this, EWEB would return sections of the project to pre-construction conditions, including the likely removal of the Leaburg Dam and the return of Leaburg Lake to river form, as it is uncertain if regulatory agencies would allow a dam that's part of a hydropower project to remain if the electricity generation has been terminated. To transfer tributary waters to the McKenzie, EWEB would create a new spillway at Johnson Creek and modify the Luffman Spillway to convey Cogswell Creek and other tributaries. This alternative would convert the near-term risk reduction measures into a long-term solution. Each alternative has substantial benefits and trade-offs, so commissioners have requested a triple bottom line assessment to evaluate the complex impacts of their decision. Considering the financial impacts, EWEB's Leaburg Hydroelectric Project strategic evaluation team calculated the upfront capital costs, impacts to EWEB's borrowing power, operation and maintenance costs, power generation potential based on varying river flow regimes, and benefits of owning renewable energy on carbon markets. The net present value, or the difference between the anticipated incomes and expenses, is substantially negative for each alternative, and the expected net present values for each alternative is as follows: a $230 million loss for Alternative 1, a $236 million loss for Alternative 2, a $183 million loss for Alternative 3, and a $188 million loss for Alternative 4. The economic impacts must be compared to the potential environmental and social impacts of each alternative. The environmental considerations include the carbon footprint of construction and the future implications of EWEB's power portfolio, how construction and a new configuration would affect the water quality of the McKenzie River, including turbidity, sediments, flow regime, and temperatures, the McKenzie River fish populations, fish hatcheries, lamprey and silt deposit populations, the wetland acreage, terrestrial and avian species, particularly during construction periods, and vegetation impacts. The social considerations include public safety, including water hazards in the canal, landslides and floods and how they affect the canal, property values, fiscal impacts like tax revenues, wildfire response and the effects of the lake and canal being removed or remaining in place, recreation, including boating and fishing on the lake and walking the canal trail, visuals and aesthetics, how local economic activity would be impacted by construction and recreation changes, impacts to domestic wells, surface water supplies, tribal resources and cultural sites, impacts to local transportation networks during construction, noise levels, historical preservation, as the project facilities are on the National Registry, and environmental justice, paying particular attention to impacts to low-income and underserved populations. The Leaburg team and consultants will present the findings of the triple bottom line assessment to the board in October, and commissioners are expected to make their decision in December. To provide your input, public comments are being accepted until October 10th at eweb.org/Leaburg Public Comment. Thank you for watching this video to learn about the Leaburg Hydroelectric Project and for participating with your public utility. Together, EWEB and the people of Eugene and the McKenzie Valley can continue to work together to guarantee future generations will have electricity that is safe, reliable, affordable, and environmentally responsible.